Augies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with another episode of Ask Dave. Today we're going to answer a viewer question and take a look at why some verticals require radials while others do not. We'll be using a number of diagrams from the ARRL antenna book, and this is the 23rd edition. I know the 24th is out now, but I'll probably wait till the 25th or 26th before I update again. After all, not that much changes in here. Antennas keep working the same way. So let's take a look at the charts. Okay, we're going to look at vertical antennas versus radials. Now, there's two basic types of HF verticals. Quarter wave, vertical, and they're called monopoles because they're not a full dipole. Dipole implies two. Di equals two, so there's two ends. This is a quarter wave. It's half of that. It's a monopole. Quarter wave vertical antennas can be multiband. They take advantage of ground reflections, wave reflections off the ground. Most ground in the world needs some help. Ground isn't all that good at reflecting. So we give it some help in the form of radials. And radials are an art all its own. Now, some examples of quarter wave vertical antennas that require radials are Butternut HF9V. I've had one of those. The Step IR Big IR, which I have right now. The High Gain 14AVQ, that was my first vertical when I was a novice. The 43-foot vertical, which underwent a vogue about 10 years ago. The DX Commander, which very much is having a vogue right now, is also an example of a quarter wave vertical monopole that requires radials. Now, there are a number of half wave vertical dipoles, and these literally, or I should say electrically, are the same as taking a plain old ordinary dipole and turning it vertical. Generally, they're multi-band. Usually they're end-fed, but not always. You can feed them at the middle. You pull the feed out at an angle away from it. But usually they're end-fed. All the commercial ones are end-fed. They do need something to work against. You can't just feed one wire to that vertical monopole. You've got to connect the other to something that is somehow representative of ground. And so they use a counterpoise or something like that. But they are electrical half-wave dipoles. A couple examples are the Cushcraft R5000, which we'll look at, and the High Gain AV640, both of which are rather pricey antennas, but then again, so are the quarter wave vertical monopoles. Okay, let's take first a look at the monopoles. Here's what's going on. Imagine you take a half-wave dipole, okay, and put it vertical. Put it vertical. This is like the string on the bow there. Okay, this line represents the RF voltage, and this the RF current. These are not individual waves. This is if you were to put a voltmeter across this and see what the RF voltage is. The RF voltage is highest at the ends and lowest in the middle, and the RF current is highest in the middle and lowest at the ends. Now, the way a vertical monopole works, is you've got a ground plane of some kind right through here, okay? And you've got your antenna sticking up a quarter wavelength in the air. It's insulated from the ground there. So the center conductor of the coax goes to the part that sticks up, and the other side goes to whatever represents the ground. Now, the ground acts like a reflector, acts like a mirror. And you will see, if you look into a mirror, you'll see a reflection of the antenna here. So the antenna behaves conceptually as though it's an image of this one reflected in the ground. Okay, and I've done demonstrations with mirrors where you can put a quarter wave antenna up here and see the other half of it represented down here, and that's how that works there. And that works great with perfect RF ground. And this is kind of what's going on in there. You've got an antenna with a direct ray. You've got this perpendicular part right here. This is close to an equilateral triangle. This reflects off the ground, a reflected wave. And if you figure the image on the thing and the speed of RF in ground, which is slower than it is in the air, you will get a complex reflection here. And this wave here is in phase with the wave up here. Okay, so this is the direction of travel to whoever is at the distant point. Okay, so it works by reflection, and the reflection on the ground assumes if you've got a good reflection, it'll work that way very nicely. Now the problem is that there's really no such thing as good ground. Okay, so we're going to have to imitate a good ground with radials. I mean, if we look at ground for common types of earth, the conductivity quality versus the dielectric constant in Siemens per meter, and so on. Fresh water is a lousy conductor, but a good dielectric. Salt water is about the same dielectric-wise, is a fantastic conductor. I love these words here, pastoral, low hills like Dallas, Texas to Lincoln, Nebraska, and so on. And then you get down to where I am here, rocky soil, steep hills, typical of mountainous terrain, a dielectric constant of only 12 to 14. The relative quality is poor. Okay, so we can actually look at a map of the United States and kind of get an idea of what the ground quality is there. Right where I live is right here, where the cursor is, and that's a 4. And if you look on the previous chart here, 4 is down here. 4 is really poor ground. So what we're going to do is ignore the ground and make our own ground. Ground plane, that is. A ground plane. The ground plane is made up of radials. A radial is something, the reason it's called a radial is because it comes out like a spoke. Okay? It comes from the radius. It's the radius of the circle of these things. It's the radius from the center out to the edge. Now this actually is a practical antenna at VHF. You can make this, the center conductor goes to this, and the outer conductor, the braid, goes to the ring that supports all these radials. And 4 radials isn't very many. Here's a chart that would take you half a day to figure out. But the idea is to think of what you can do if you have a 1 wavelength worth of wire to make into radials, 2, 4, 8, 16, or 32 times the wavelength to make in radials. And note, you don't have to make the radials a half wave. You can make them very substantially shorter. And so, for example, if you have 1 wavelength of wire, you can make 4 radials down here that are a quarter of wavelength long, or you can go up here to 8 that are less than a quarter, about 1.25 wavelength long, and find that you actually get an improvement in the signal improvement from down here 0, which is your baseline. You take, instead of making 4 radials each a quarter wavelength long, you take that same amount of wire and make 8 radials each 0.125 wavelength long, and you've improved your signal. Well, if you put a little bit more wire in here, you see you get up into the point here where adding more radials doesn't make much sense. And that point happens to be around 32 radials. Okay, going from 32 radials, if I got 4 lambda here, if I made 16 radials at a quarter wavelength, versus 32 at a quarter of a quarter, or I'm sorry, half a quarter, 0.125 here, I actually get in improvements. So the message of this chart is simple. More and shorter radials is better than fewer and longer radials. Okay? And once you get up past about 16 to 32 radials is 4 dB over the baseline here. If you go from 16 to 32, you don't quite gain a dB. You go to 64 radials, you gain a little bit more. 128 radials, you hardly gain a thing. So where's the sweet spot? It's somewhere around in here, between 16 and 32 radials. Okay? If you can put that many radials, and they don't have to be very long, okay, you can put them in here. Now, my radials are all different lengths, and that seems to work well because the radial length here is in terms of wavelengths. If you have multi-band antenna, it's going to work differently. So what we've talked about here is how we've got this half up here, and we are using the radials to create a good ground plane for the reflections to take off appropriately. Now this shows, this is, let's see, this is a quarter wavelength, so this is more than half a wavelength. The radials might only go out to here, but you get the same sort of effect. And most of the U.S. has got really poor ground. Some places are good. By the way, salt water is fantastic. So we took a look at, if you're going to be in a rice paddy where you put your antenna, you've got very good ground there. Not as good as 1,000%, or this would be actually 100%. Okay, flat desert and cities. I think there's some sort of a commonality they're trying to make electrically here. Rocky Mountains, pastoral land, rich agricultural land, rice paddies which are flooded, and so on. Okay, so we've looked at these. Now let's take a look at electrical half-wave vertical antennas and see what we can see here. Now, this is shown in the book as though it is just a standard dipole, which is center-fed, turned vertically, and one end barely kind of off the ground a little bit. Actually, here's another case where they move it up a little, and you start to get these other lobes in here, just like you do with a dipole if you go up too high. So again, the center at a quarter wavelength gives a very nice pattern. But this is a half wavelength high. Now, do you have to feed a dipole in the center? Of course not. You can feed a dipole off-center fed, you can feed it end-fed, and so on. So let's take a look at a classic end-fed dipole here. This is the Cushcraft electrical half-wave R6000 antenna. Okay, they call these radials down here, but they're not. These are too short to be radials. Because they are too short, they are capacitive in nature. So this is a capacitive counterpoise. These are not radials. It just gives the antenna something to, quote, work against. And then these things up here are various structures to support multiband operations. So in here, there is a balun, just like a 49-to-1 balun or something that my antennas would use, and it feeds the end, because this is a half-wave, electrically a half-wave dipole. Okay, so the end of it, if you remember looking at the right here, the end of it has low current, high voltage, so the voltage over the current from Ohm's law is going to make this a very high impedance point. So we can look here and we see that, did I skip chart? I was down here. Okay, this is the electrical half wave right here. And it's end fed at a high impedance point right there. But this thing, you got to do something with the other wire, the ground wire, or the shield, the coax shield. So you attach it to this capacitive counterpoise just to give it something to work with. This is a big capacitor. It's a very reactive counterpoise. And then this is also grounded right here to bleed off any static charge. And the way the balun works at DC, this is connected through to this, so static charge up here can bleed through on that balun and get to ground. Okay, let's look at, this is from the R6000 manual. They talk about attaching the matching network and the radials. The matching network is that balun that allows you to feed up here, which is at the high impedance point. It calls these radials, but they're much too short to be real radials, so they're capacitive. Okay, and this shows it a little bit more clearly. Here is the feed point right here, and it goes up to here through the balun, and then this is on the other end of the balun. The other end of the balun needs to connect to something. Now, in the My Antennas case, they've got a terminal you could connect to ground or a counterpoise, or you can just use the outside of the coax to get to the ground at the lightning arrestor. Okay, so basically we've got this idea that verticals can have radials or not have radials, depending on whether they're a quarter wavelength or an electrical half wavelength. By the way, I should talk a little bit about shortening antennas. This shows a full dipole. Well, we know that if you put loading in here, inductance, it makes the thing electrically longer, so we can actually shorten up the antenna on either end. It will make it higher Q, yes, but it will allow you physically shorter. Another way you can do it is put capacitance at the ends. So inductance in the middle or capacitance at the ends will allow you to shorten those antennas. Parting thoughts. Verticals can have low radiation patterns. They can be great for DX if you want to do that or get long distances. I think most people find that in casual operation, a dipole and a vertical work about the same. Now, quarter wave and half wave, lambda's wavelength there, quarter wave and half wave antennas can both perform well. Now, advantages of verticals, they're good DX antennas. And they don't require large land areas. You don't need a full half wavelength to put in a good radial field. You can do it with a quarter wavelength or less. Okay? With radials, you don't have to have them in every direction. If you've got some sort of an impediment like a building, it'll still work. Now, one of the disadvantages of the radials is that verticals tend to be more expensive than a simple dipole, simply because it's got to hold itself up. So you're often dealing with aluminum tubing rather than just wire. If you got a tall tree, you can make the wire hang from the tree, but then you've got to put out the radial field, so you're going to put out more wire. And there's nothing wrong with homebrewing a vertical. It's usually easier to homebrew a single band than it is multiband, but there are plans out there for multiband antennas. So, I hope that helps. Okay, we had a little fun talking about vertical antennas today. Lots of options that you can do. There are many, many models to choose from. One time you might want to use the no radial electrical half wavelength vertical is if you have a pretty small space and a pretty small backyard. You might want to put it up on a pole so the bottom's about 10 feet off the ground or so, but do what you can. and have fun with it. And make sure that nobody can get up there where they can touch those so-called radials or counterpoise parts, because they are electrically active. They will have high voltages on them. So the advantage, of course, of the full-size monopole, like my Step IR, Big IR, has a quarter wavelength, an actual quarter wavelength of a copper tape that is quarter wavelength even on 40 meters, so it goes up quite a ways, is that they can have outstanding propagation with low propagation angles and get very long distances. But you know what? Any antenna is better than no antenna. So if you can put up something simple that works, like a dipole or whatever your homeowners association will allow, you can have a lot of fun on ham radio with that. Tomorrow we have a video on how to build the base for a hex beam, and then we're going to take a look at the latest firmware update for the ICOM 7300, and we'll walk through all the steps of updating firmware on an HF radio. Again, we'll be using the reference station as our example, but the steps will apply to just about any of the radios that are out there. All right, so if you'd like to support this channel financially, please go to dcasler.com/support. And until we next meet, 73.